Okay, everyone, this video we're going to be looking at one of the weakest intermolecular forces, London dispersion forces. So what I have here, I've got a picture of a methane a molecule here. There's two of them side by side. And you remember that methane has a difference electronegativity between carbon and hydrogen of 0.4, making it a relatively non-polar bond here. And as a result, the whole molecule is nonpolar, so there's no real charges around the molecule. And what happens though is that we still have some attraction between methane. We can actually form liquid methane. So there must be some attraction between these molecules. Well, what happens is, remember, we have all of these electrons that are being shared in these different bonds, and they're moving around all the time. And what happens is every now and then you might have an unequal distribution of the electrons. And some electrons might end up more on this side than on that side. So that would make this side a little bit negative and this side a little bit positive. And then just a moment later, incredibly fast, this disappears, and then the charges disappear as well. So it's a very short-lived, fleeting intermolecular attraction. So it doesn't last very long, and because it's such a short period of time and it's such a tiny amount of unbalance in charge, there's hardly any attraction. Now this happens in any molecule. Any molecule will have London dispersion, but the London dispersion forces are usually masked by the other stronger ones. You don't even know that these are here, but they do occur. So let's look at this a little bit more detail. So if I did have this occur, this imbalance of electrons, so you can have a little bit of a negative, a little bit of a positive. Remember, it's a very short, very weak. What happens is we've got electrons over here in the adjacent atom, and what's going to happen is the electrons are going to be attracted to the positive charge. And as a result, it's going to make this end of this molecule negative. This is called an induced charge. And look at this, we have a little bit of attraction between the molecules. Now, over here on the original atom, these electrons are going to go back to where they were before, and the charge will disappear. This also means that there's no reason for these electrons to be attracted, so they'll go back to where they were before as well. And this charge will disappear. So again, it's a very, very, very fleeting, short-lived, and weak attraction between adjacent molecules. So this is what you have in your note. So again, the key thing here is it's temporary. So it's a very short-lived. Okay, so that temporary unequal distribution is only fleeting, and then again, a few seconds or microseconds later, you go back and the charges disappear. So it happens again in all molecules, but they're so weak, they're masked. So if I had, say, for example, water is going to primarily have hydrogen dipole-dipole bonds or forces between molecules. You still have a little bit of London dispersion, but so weak you can't even tell it's there. Okay, so let's look at the size of molecules. So I've got here different molecules, and what happens here is we've got different boiling points for each of these. So all of these are hydrocarbons. They're made up of carbon and hydrogen. Let's look at the boiling point. So if I was to try to boil methane, it would happen at minus 162 degrees Celsius. What does that mean? Well, at minus 162 degrees Celsius, there's hardly any energy, and already these molecules are falling apart. So the forces between the molecules must be extremely weak in order to be able to do that. Then I've got this. This is propane. This is what you'd be using in your barbecue. And propane, it vaporizes at 42 degrees Celsius, below zero, so minus 42. Then over here we've got octane. Octane is a component of gasoline, and it has a boiling point of 125 degrees Celsius. So at 125, it has a little bit more attraction, so it's a little bit harder to separate these molecules. And then we've got wax, and wax has a melting point, depending on the type of wax, around over 200 plus degrees Celsius. And look at it, it's a huge molecule. So clearly something is going on here. The larger the molecule, the more intermolecular attraction there is, the more these molecules are sticking together. Why is that? Well, they don't have dipoles. There's no charges that are like long term. So the only thing that could be occurring for all of these is London dispersion. And what happens is, if you're a very large molecule, you have so many electrons, the chances of some electrons being on one side for a short period of time is much, much more likely than having electrons unequally distributed in a methane. So when you look at these molecules, the larger they are, the more attraction there is, because of more temporary uneven distribution of the electrons. And the more attraction there is, the harder it is to separate molecules, so the higher the boiling point. So again, the number or the strength of the London dispersion force depends on the size of the molecule, the number of atoms. The larger the molecule, the more likely the uneven charge, and the stronger the attraction. So you might be highlighting these terms. And again, this is a little chart. You can see here how quickly the intermolecular forces add up with London dispersion. So let's look at a good summary of all of the intermolecular forces. So the last one we just saw is the first one we're going to be going through, and this is going to be the London dispersion. So London dispersion happens in all molecules, but we really only see it in non-polar molecules because it's being masked by the other ones. And what happens is, it's a temporary and very weak uneven distribution of charge. You get those temporary dipoles. And what happens is, larger molecules have more attraction between them with London dispersion than smaller ones. That's why wax is a solid, and that's why methane is a gas at room temperature. Okay. Then we had this. We had the dipole-dipole forces. Now, in order to have a dipole-dipole force, you need to have charges on the molecule. So you need to have a polar molecule. Now, the polar molecules are going to have these dipole-dipoles between them, the negative and positive ends. If you're very, very, very polar, that means you have a lot more charge. And that usually happens with hydrogen bonding with nitrogen, oxygen, or fluorine. What happens then is you've got a super dipole-dipole, I call them. These are the hydrogen bonds. It's like an extreme dipole-dipole. So you're going to see it in HNOFs. HNOFs mean hydrogen, nitrogen, hydrogen, oxygen, hydrogen, fluorine. So in other words, ammonia, water, and hydrogen fluoride. And the bigger the difference in electronegativity for all of these, the more charge you have, and the stronger the intermolecular forces, the more attracted the molecules are to each other. Now, a question I often get asked by students is, hey, this is cool that you have all these intermolecular forces. How strong are they really? So let's look at a little chart over here. This isn't a perfect chart, but it gives you an idea of roughly how things work. So what happens is, if I look at all of the different forces, what's going to happen is the true bonds, covalent bonds, ionic bonds, are very strong. They'd be way over here. Okay? Now, the intermolecular forces are extremely weak. So they'll be way, way, way at the other end of the spectrum. They're somewhere over here. And then if I look at the intermolecular forces, you're going to have these three different ones. So the weakest one, remember, is going to be the London dispersion because it's just temporary. Then we had dipole-dipole. We had the true charges in the polar covalent bonds, polar molecules. And then if you have a hydrogen with a nitrogen, oxygen, and fluorine, they have an extreme dipole-dipole hydrogen bond. And all of these are intermolecular forces between molecules, and they determine the physical properties of a substance like melting point and boiling point. So that's it for intermolecular forces.